Sorry about that. My phone filled up, so I had to delete my old chemistry videos. Anyways, what we were talking about is kinetic energy. And this car at a human scale seems to have no kinetic energy. But it is made of particles. And those particles are moving. They are vibrating. So we'd put like little vibration lines around them. Oh, they vibrate so much, right? And that vibration is considered a movement. So these particles are actually vibrating. They're actually moving. And any kind of movement, it doesn't have to be like across the universe. It can just be wiggling. Any movement at all is considered kinetic energy. So even though at the human scale this seems to have zero kinetic energy, it actually does have kinetic energy, because at the atomic scale, the atoms are wiggling, the atoms are moving, so they're individually moving, and all that would add up to an amount of kinetic energy. So that's kinetic energy, and this is a solid. And what that means is that the particles only wiggle, right? But if we take a liquid like my delicious coffee, let's take a sip. Still liquid. So if we think of a liquid instead of a solid, now the particles aren't just moving, they are able to move around. They can't fly, but they can wiggle around. They can go from left to right. And the reason why is because there are intermolecular bonds holding these things together. So you can think of there being bonds here and bonds here and bonds here, and we can call them dispersion forces or van der Waal bonds or whatever you want. There's a bunch of terms for it. But these things that hold, and they'd even be here, these things that hold stuff together want to be a specific distance away from each other. Because the outside of each of these is negative. So if you have negative and negative, they actually want to repel. But the problem is if this guy goes this way, he gets close to here, and this guy pushes him back. And if this guy goes this way, he gets close to here and pushes him back. So all these forces are actually constantly readjusting, because it gets stronger as this gets closer, because those outer electrons would push it back more. So it gets stronger, and then it gets weaker, and then it gets stronger, and it gets weaker, and it kind of moves around. And that's why they vibrate, because they're actually being pushed and pulled by these forces around them. But if you give them enough energy, really heat them up, because kinetic energy, of course, is a measure of kinetic energy is temperature, actually. If you really heat it up, now what they can do is they can actually not just vibrate, they can wiggle and relocate. So this one can kind of squeeze between these two atoms and now squirt out on the other side. Now the dispersion forces will actually keep it from heading all the way out, right? So it'll relocate over here, still vibrating, and it would want to leave, but there's also forces attracting it back. So those dispersion forces, those van der Waal bonds, aren't just repelling, they're also attractive too. So all of these can kind of now wiggle around and move all over the place and slide past each other. And that makes it a liquid. So in a solid, of course, they just vibrate. In a liquid, like the coffee inside of this clearly is solid, but the coffee inside is liquid. They can start sloshing around, so they get enough movement that they can now kind of wiggle and slosh and slide past each other. And then we get to what we've been waiting for, gases. Now, gases is what happens when you take a liquid, this kind of thing, and heat it up so much that, boom, they can actually defy gravity. So at that point, the arrows that I would use are these kind of arrows, and those kind of arrows, and that kind of an arrow. And now they can actually fly. They can defy gravity. They have so much energy, and that's why they have no shape or form. We can't make them be a certain shape or form on their own. Now we can contain them using things like, bottles and balloons and other things that can hold gases. but on their own, they will not take a shape. They can't drive. I like to think of gases as if you were to take an actual sports car and tape the gas pedal down, but rip the steering wheel off and just see what happens. That's a gas particle. It flies off and then bangs against something and flies somewhere else and bangs against that and flies somewhere else and bangs against that. And that's what the life of a gas particle. So gases are made up of atoms that have tons and tons of kinetic energy. And the way you get a gas is you take a solid or a liquid and concern it, heat it up, give it tons and tons of energy. Now, there is another state of matter, and we know that you have solids, and solids are when the particles just wiggle, they don't move around. And we know that you have liquids, and that's when they wiggle and they slide past each other. And then we have gases, and that's when they wiggle and have lots of kinetic energy. Right. There's actually another one that should be at least mentioned, and that is plasma. Plasma is, the kind of classic version of plasma is junk on fire. So that's like the center of the sun, or flames, right? There the particles are going so fast that they could be changing. They could be going through chemical reactions. They could be kind of wiggling and traveling so much. So they're like super wiggling and they're flying around with even like longer, faster movements, that they do things like they give off light and will become another element and stuff like that. So plasma is even higher than gases. If you heat up a gas, you get plasma. And that just means it has a ton of energy. So I should mention that plasmas exist. We're not going to be spending a lot of time with that state of matter, but a completist should at least acknowledge its existence. So gases are simply the state of matter where junk goes fast, and that's why they can defy gravity and go all over the place. They don't have a definitive shape, and the hard thing about gases, and we'll butt up against this for this entire unit, is they're really hard to catch, right? Because they're moving so fast and they're so small. I technically have gas trapped in my hands, but I also know that the gas that is in my hands is escaping and new gas is coming into my hands. This isn't a perfect seal, right? And I can't do things like grab it with my hands, jump, into a lake, and then breathe the air that was in my hands. Because the second I go jump in the lake, the gas is going to leave, and I'm just going to have wet hands, right? And that makes labs, especially at home, pretty difficult. So we're not going to be doing a ton of gas labs at home. Sorry about that, but lucky you. Now, the final thing we have to do is we have to answer the point. So if I remember correctly, the point was quite simply how our gas, as in that state of matter, and kinetic energy related. And the answer is, of course, gas particles have a lot of kinetic energy. Or a lot of movement, since kinetic energy means movement. And in fact, every single particle on this planet is moving, except if we could get it to absolute zero, then it would stop moving. But, we haven't been there yet. Maybe in my lifetime, definitely in your lifetime, we'll get there, and things will be different. But as of now, everything has at least some kinetic energy, because the particles of everything are at least vibrating. Even if they're vibrating slowly at very near absolute zero, they're still vibrating. So they still have kinetic energy. There we go. Good luck.